cyclic, chiral isomers, holoalkanes, we've seen the diverse range of molecules that come from carbon's ability to catenate. But how have we seen it all? Introducing carbon nanotubes, essentially a hollow cylinder polymer made 100% of carbon monomers and covalent sp2 orbital bonds. The benefits? Endless.
To appreciate this macromolecule's applications, we first need to understand what nanotubes are. Scientists understand carbon nanotube properties by visualizing them as rolled-up graphene, a planar carbon material, and through this, understand how carbon nanotubes can either be single or multi-walled. But this model isn't exactly what happens in carbon nanotube synthesis. So what does? Research has established 3 common methods, one of which is chemical vapor deposition. Research by Brook and Mitra in 2006 outlines general procedure where a hydrocarbon gas, like ethene, undergoes thermal decomposition at 700 degrees Celsius, using heat as a reagent and breaking intramolecular carbon, hydrogen, and carbon double-bonded carbons. The products are active free radicals, new hydrocarbons, and elemental carbon. The carbon atoms are what's most important because they deposit into small pores containing transition metal catalysts like iron drilled into quartz or silicon substrate. Carbon double-bonded carbon molecules will then first cover the surface of the catalyst, then allowing us to undergo addition polymerization when carbon monomers bond together and rapidly form the nanotubes, whether that be via root or tip growth. And of course, depending on the diameter and angle of the pore, this will have effects on the conductivity and different properties of the nanotube, really indicating the nanotube's flexibility and modifications.
But what makes this macromolecule unique? It's mainly these 3 properties: the intramolecular bonds, the molecule's sp2 hybridized orbital spaces, and the pi bonds that make this nanoparticle mind-blowing to 21st century research. Carbon atoms have small atomic radii, so the carbon-carbon in nanotubes form strong bonds due to their shorter bond length. Carbon-carbon is also covalent and nonpolar when their delta electronegativity equals 0.
So its nonpolar characteristic implies hydrophobicity, allowing for nanotubes applications in areas like nanofiltration to remain inert in aqueous environments. Carbon presence in nanotubes are also what produces strong covalent bonds, requiring high energy to break them. So experiments like Roth et al. Support the positive relationship between bond strength and energy required to break those bonds when we discover multi-walled carbon nanotubes' tensile strength being upwards of 100 times higher than steel and 3 times higher than materials like Kevlar, and being generally stronger than their single-walled counterparts. Further, the sp2 hybridized orbital space is what builds in the trigonal planar stereochemical structure in every carbon atom. This is what builds the geometric network of pentagon and hexagonal gaps in the nanotube, in which NASA has been investigating when nanotube semi-permeability has the potential to create highly selective water filtration systems that are synthetically accessible and 6 times faster than nature's filtration proteins aquaporin. And finally, the many pi bonds that form as a result of each carbon's need to satisfy the octet rule transform into a free-flowing sea of electrons that has significant effect on the carbon nanotube's overall conductivity. The relationship of delocalized electrons with conductivity are affected by the diameter of a nanotube, which research has shown is template setup dependent.
With carbon nanotubes as a hallmark of chemical nanoscience's innovative solutions to the wider world, who knows where research will take us in the coming years?